Started by? Is it started? Not it. Yeah, now I think it is.
Started, sir.
Yeah, yeah. Okay then. Welcome to today's class. I think around 20 people are there. So last class we were discussing about this adiabatic operations, right? So 2 marks question, important question is what is adiabatic operation? Adiabatic operation is an operation in which the system does not give heat to the surroundings nor it receives the heat. So it is perfectly insulated. That's what we mean by adiabatic operation, right? So here important thing is if the reaction is exothermic, then the total enthalpy of the product will be equal to the enthalpy of the reactants plus the heat of the reaction which is being liberated. That heat you have to add to the reactants to give you the enthalpy of the product. Whereas if the reaction is endothermic, then the total enthalpy of the product will be equal to the enthalpy of the reactants minus the heat of the reaction, because you are giving the heat or giving out, right? So these two things is very important. Then we saw this derivation. We are doing an energy balance. Input is output plus accumulation plus disappearance. Accumulation is not there because we are going for a steady state. Input enthalpy is 0 because the reference temperature is 25 because that is the standard. And if your temperature of the entering feed is also 25, then it becomes 0. If your entering feed is having some temperature other than 25, then this will have some value, right? That you keep remembering it. Here I am assuming that my inlet feed, where is it? Yeah, inlet feed is 25. So as same as the standard, that is nothing but the reference. T1 is the reference temperature. So if your inlet feed is equal to the reference temperature, then this will be 0. Otherwise, this will have some value. Am I right? So that you remember. Here I am assuming it is C. Then the enthalpy of the leaving stream is how much it is being converted. How much it is being converted. That is the enthalpy of the products. This is the product. XA is the product which is being formed from the reactants. So, and then how much is unconverted? 1 minus XA becomes unconverted, whereas XA becomes converted to the product. 1 minus XA becomes the unconverted or the reactant which is unconverted, that into its enthalpy. So, if you put the same CPDT, then energy absorbed will be equal to the heat of the reaction into the conversion, right? So all will have a unit of joules per mole. This also will have joules per mole. This also will have joules per mole. So if you substitute in this equation, then input is 0, accumulation is not there. So if you rearrange, you get XA is Cp dash delta T divided by minus delta H R1 minus Cp into delta T. So this entire equation is nothing but, you know, the delta H R1 at a particular reference, and then integral CPDT or whatever you call delta CPDT is nothing but delta H R2. Delta H R2, that is the heat released by the reaction at T2, and Cp star Cp dash delta T is nothing but the heat raised to the feed stream, right? So if your these two equals, then your XA becomes 1. That's the important thing. That is the heat released at the that is minus delta HR2. That heat of reaction at a temperature T2 becomes this Cp dash delta T. Then your conversion becomes 1. For suppose if you are having the CPs of same of reactants and products, then instead of Cp star, you can put as Cp, only one particular Cp. This is a very important expression which is called as an adiabatic line or material balance line. So if you draw XA versus T, because XA versus T, So Cp by delta HR becomes the slope. Cp by delta HR becomes the slope. And then if the slope is positive, if the delta HR is positive or negative, delta HR is negative for a exothermic reaction. Therefore, negative of a negative becomes positive and the slope becomes positive. That is what you get like this. And delta HR is positive minus delta HR becomes negative here. Therefore, this is for endothermic reactions. And if you are having some inerts, then you see the vertical line is for isothermal condition. And if there are inerts, both exothermic and endothermic, then these two curves tends to the isothermal condition. That is an important thing. Why inerts? It is tending to this particular thing. Can any idea? Or if there is a decrease in inerts, then both is moving away from this particular lines, right? Yeah, here I asked one question, why the increase in inerts is increasing this side to the isothermal? It is because of specific heat. Specific heat is increasing. Therefore, it goes to the isothermal, right? So we have to, now we are having the material balance line and the energy balance line. Now, based on this, how we can decide what size of the reactor is being used. That is what is this. Till this, I think in the last class we discussed, this we are discussing today. Size of the reactor required to achieve a given conversion. Now you see, these are the XA versus T. Again, I'm drawing with the XA versus T. And these are the rates. These are the rates, right? This is how you are getting these rates. It is coming from your material balance line. So now, if you are assuming it is a plugged flow reaction, this reaction is happening in a plugged flow, which is endothermic. So endothermic means where the slope will be endothermic means delta HR will be positive. Therefore, minus delta HR here, minus delta HR becomes negative. Therefore, XA, the slope of CP by delta HR becomes what it becomes negative. Therefore, if I draw a graph between XA versus T, you get a negative slope. So that is what negative slope, how much it is going, what slope it is going. It is nothing but Cp by delta HR. So you know what is Cp and you know what is delta HR. Based on that, this slope, we draw this particular line, right? We draw this particular line from a particular temperature at which it is happening. So this energy balance line, this is the energy balance line, and it is touching this particular curves, material balance curves or the rate curves. So if you want to find out the temperature or volume or size, generally this optimum progression, we earlier itself discussed about this optimum progression, right? Optimum progression is nothing but the temperature progression which minimizes the size. Which minimizes the size in the sense V by Fa naught. That is what is the size. V by Fa naught is tau by Ca naught is equal to some equation for a laminar flow and mixed reactor. It will come. So minimizes the size in the sense here it is V by Fa naught. That you remember. Fa naught, you know, that is the flow rate. Then we can calculate the V, right? So here, if you go in this particular line, if I am drawing this energy balance line, that means that if I am in this particular line, my V by Fa naught will be minimum. That is the size will be minimum. So how to find out that size? That size is nothing but this is touching, this is RA1 and RA2, RA3 and RA4. So this energy balance line is touching RA4, RA3, RA2 and RA1. So correspondingly, you can take your XAs. This point is XA. This point is also XA. This point is also XA. I'll just do that. Now this is, let it be XA, one XA, and this is also one more XA, and this is also one more XA. So for this corresponding XAs, you are taking, this is 1, 2, 3, and 4. This is particular T. This is particular T. Now what we need to do, if this is a plug flow reactor, we know that the area under the curve will be equal to V by Fa naught. That is what here. So we can draw, this is versus XA minus 1 by RA, 1 by RA versus XA. This is XA. How you are getting this XA? This XA is nothing but the interpoint of this. This XA is what you are going to get. That you put on the y-axis, and 1 minus RA on the y-axis, because you are getting this RAs, right? 1 by 1 is 1, 1 by 2 is 0.5, 1 by 3 is 0.3, 1 by 4 is 0.5, 0.25. So 0.4 to 1, you draw a line, and then there will be a point here, there will be a point here, there will be a point here. You try to join that particular point. So if you want 60% conversion till 60%, you take that line, and this area under the curve will give you V by Fn0. This is the way you need to calculate the volume of a PFR, which is endothermic. Here it is endothermic. How I know it is endothermic? From the energy balance slope itself, I can find out. This is the straight, this is for the isothermal, and this is for the exothermic. So based on how this line is going, you can know whether it is an endothermic or exothermic. Now, if we want exothermic reaction, for the same thing, let you have again RAs, different RAs, and this is an exothermic reaction. We know that for an exothermic reaction, when this particular curve will go down, this particular curve will go down like this, and the rest of the thing will have a maximum and then fall to this particular thing, right? So it goes near to this and then equal. You have a locus of the points for exothermic reaction. So for a exothermic reaction, what is happening to the slope? For a exothermic reaction, we know that delta HR is negative. Negative of negative becomes positive. So if I draw a curve between XA versus T, then the slope of delta Cp by delta HR becomes positive. So with a positive slope, with a from particular temperature, I draw a line. This is a straight line cutting the different RAs, that is material balance. This is my energy balance line. This is my energy balance line, and this is my material balance line. This is my material balance line. Generally, this line is called as the operating point or operating line. Operating line, right? So in I think in what is that, mass transfer, get more of this equilibrium lines, operating lines and all. So in here we call this adiabatic line as the operating line. So where this operating line is meeting this what do you call grade curves, you have to find out. And again, it is touching here, it is touching here, it is touching here, it is touching here. Therefore, you calculate XAs, here, and based on this XAs and this rate, this is minus again XA and rate. Then you draw a line where you want the point, where you want the conversion. At that particular point, you put a vertical line, and the area of this particular thing will give you the plug flow reactor volume. So this entire thing, it's almost is equal to almost like a, what is this curve? Autocatalytic reactor. We know that for autocatalyzed reactor, instead of one PFR, you put a CSTR till this particular point, your area will be minimum, and then go for PFR, which minimizes the volume instead of one PFR, right? So that you have to keep in mind whenever that you are getting a U-shaped curve like this, and especially for a PFR it is there, instead of calculating the entire curve, so try to find out what is this particular rate and what is this conversion. Till that particular conversion, please put you put a MFR, so that the MFR in the sense it is the area of the rectangle here. Therefore, and from this you put a CSTR PFR instead of one PFR, then your V by Fn0 will become much lesser, right? So this is for exothermic plug flow. Now, if it is exothermic mixed reactor, you know that mixed reactor, it is the area of a rectangle. The same again, exothermic in the sense you get a positive slope, and these are the rate curves. This is the rate curves, These are the ideal rate curve, and this rate curve will go on to that asymptote to that particular thing. Now, at a particular temperature, you know what is the temperature. At that particular temperature, you put a line like this, and then see which this particular thing is bisecting that. And this is the point which is this line is bisecting with this particular thing. So that point you take, that is the conversion. That particular conversion is 0.8. So you want for a 0.8 conversion. This is the slope minus RA versus XA. You see what is this all XAs, where it is being touched. And then based on that, you want 80% conversion. At a 80% conversion, instead of going for area under the circle or area under the curve, you go for a rectangle. So this will become your area of this particular entire. This also will come. This is for the mixed flow. If it is endothermic, then your slope will come like this. Slope will go like this. Again, you see which point you want. Again, you draw minus 1 by RA versus XA and see whichever point conversion you want and put a rectangle, right? So this is how you have to find the area of or the volume of the reactors, both for, I'll just delete this, both for exothermic and endothermic plug flow reactor and a mixed reactor. Important thing is plug flow reactor, you need to calculate the area under the curve, whereas mixed reactor, you need to calculate at a particular point the area of a rectangle. What point, how you fix this point? It depends on what conversion you want in that particular reactor. Here also, this point is fixed by the conversion, what conversion you want. If it is 0.7, then you draw a still line, this line will extend, and this also will be the extra PFR, right? Yeah, any doubt here? So remember, if it going to the your left side, then it is endothermic, and if it is going towards your right side, then it is exothermic, right? Any doubt here? Can I go for the next thing?
So
Yeah,
that,
yes,
sir,
yes.
the last
Yes.
curve graph could you explain, sir? The third
Can I?
graph.
Yeah, I'll explain again. I know you won't understand this. Yeah, I'll explain this. Now, this is for exothermic. Exothermic in the sense it is positive. So like that, you are having different curves. You are having, this is the rate curve, ideal rate curve. It goes like this. And for one, it will almost be closer to that, but it won't touch. That's how you have to draw. This is also closer to that, but it won't touch. Like that, it goes on. Like, so it will have a highest value and then goes down. Now at this particular point, you know what is the temperature. From this particular temperature, you draw a slope. Slope will be given by that Cp by delta HR. So based on that, this slope is cutting this particular rate curves. This particular rate curves, it is being cut, right? So what rate curves it is being cut? Corresponding XAs you take. Corresponding XAs you take. That is what this X is. What rate curve it is cutting? You take 1 by minus 1 by RA, right? Then we need to, in this particular problem, they will tell it is 80% conversion is required or whatever it is. So whatever conversion you require, if it is 80%, then draw a line. Draw a line, right? Till this, even for PFR, it is same. In PFR, what you do is the area under the curve, that is what you will put. The area under this particular curve till whatever value you want. But in MFR, what you do is, it is not an area under the curve. At this particular point, you draw a vertical line, a horizontal line, and a vertical line. Sorry, I didn't get the vertical line. Yeah, this is the vertical line, and calculate the area of this rectangle. Area of this rectangle is nothing but you know what is this length and what is this length. This multiplied by this will give you the area of that rectangle. Here, one important thing is plug flow in the sense you need for the same thing. This is exothermic plug flow if it is MFR for this. what we need to do? For a plug flow, you calculated the area under the curve. So for this particular same conversion, you draw a rectangle here. So this entire thing will be equal to your area of or V by F naught for MF. For area under the curve will be equal to area of a volume of a PF. Yeah. Any doubt? Did I clear your doubt or still you are?
Yes, sir.
So here important thing is
Sir.
MFR in the sense it goes to a point. At that particular point, what is this? Because in MFR there will be only one rate. That is why you are having a rectangle. Whereas in PFR you are not having any rate because rate will depend on the length of the reactor. Am I right? Because as it moves around, the rate will change in the MFR, PFR. In the MFR, you will have only one rate. That rate is nothing but the concentration at that particular concentration. The concentration inside is equal to the outside. Therefore, you get only one rate. That is why you go for an area of a rectangle. That is the main concept. Whereas in PFR, it gradually changes. Gradual changes in the sense you have to take area under the curve because there will be integral sign there. Okay. Because 1 by RA, 1 minus 1 by RA versus XA, why you have to take this rectangle? Can anyone tell? Because your expression for what is that? V by F naught. V by F naught is equal to XA by minus RA, right? This is the expression for MFR. Now, if I take this particular thing on the x-axis, this becomes minus 1 by RA on the y-axis, x into y, right? X into y is nothing but this is y into x. That is nothing but area of a rectangle. That is why you are putting this rectangle. That is the basic concept because it comes from the material balance. That is your equation. Whereas here, why you are taking area under the curve? Because V by F naught, same thing, is equal to integral dxa by minus RA. Minus RA. So you are taking 1 by RA on the y-axis, x on the x-axis. So you need to find out this integral. Integral is nothing but the area under the curve. That's the basic concept why we are going for a area under the curve and rectangle. If you want the same thing, exothermic reaction for this particular thing instead of PFR, if it is an MFR, you draw a straight line here, then calculate the entire area here. Yeah. Does it make sense, ma?
Yes, sir.
Yeah. Shall I go for next slide?
Yes,
Yeah.
sir.
Any other doubt here? Yeah. Good question that girl asked. How you fix this particular thing? Yeah. Any other? I'll go ahead. Now, how you fix this fellow? This fellow is very difficult. From what point you are going? What point you are going? This plays a very important role. This temperature or whatever you call, how you fix that? That again, for a PFR, for a MFR, in PFR, what you do? I'll just discuss this and then go for that. So these are the notes. Tabulate the rates of various values of XA along this adiabatic line, and then construct minus 1 by RA versus XA plot. Integrate between XA is 0, that is what XA is 0, and XA is final, and then measure the area under the curve, which gives V by F. For MFR, use the rate at the conditions within the reactor. You know, in MFR, there is only one rate, whereas in PFR, you get different rates based on the length of the reactor. Here, only one rate. Therefore, integrate between the limits of that. One rate means only one conversion we will have. At that particular conversion, you draw a line, find the size, measuring the rectangle area, right? Right. Now, what is this? What is this is XA versus T. How you are going to fix this point, this fellow? How you are going to fix from where you have to start? That again is very tricky. It's not that easy. for a PFR, you have to go for a lot of trial and error. And then because you have to see a lot of trial and error, I can draw like this, or I can draw here also. I can draw here from here also. I can draw from here also. I can draw from here also. Straight lines, parallel lines. But how you fix this? For a PFR, you need to go for what do you call trial and error and see, calculate if it is drawing this, then draw this type of lines. For this particular thing, draw this kind of lines. For this particular thing, draw this kind of lines and see where your V by F naught is less, right? So at that particular point, you have to fix. That is what here it is. Where you are going to fix this? This is the correct inlet temperature. If you are going away from this, again you calculate V by F naught, just like this. You have to draw for each one curve like this and see what is V1 by F naught. This is V1 by F naught, V2 by F naught, V3 by F naught. So based on that, you have to calculate. If you put your temperature from here, then your XA, this is the desired temperature. 1 second. I'll take a break. So sorry for tech call. Here, this is the exact temperature. If you are go towards your left side, then your V by F naught will be less, and towards your right, your V by F naught will be more. But again, how you fix it is by trial and error. That is for a plug flow, right? So very important. Again, for a mixed flow also, it's not like a trial and error. For a mixed flow, it's not like a trial and error. Can anyone tell why for a mixed flow it is not like a trial and error? For a, I'll just go back to this. Card again, come back. Yeah, for a what I'm telling you is for a mixer flow, it will be sorry, for a plug flow, it will be like a trial and error. How you are going to fix this particular inlet temperature? But for a mixed reactor, it's not like a trial and error. It's just a point. You can find out. How you can find out? Because in plug flow, yeah, anyone want to tell? Can you make a guess why here it is going to be a trial and error? Just like here, how it is going to be. Then we have to find out the different V by F naught, and whichever is the minimum, that particular temperature you have to take for a plug flow reactor. For a mixed reactor, it is not like that. So again, you draw a different temperatures. Here, one important thing is this is XA versus T plot. Now, for the XA versus T plot, you know what is the conversion which you want? This is the desired conversion. This desired conversion will meet this particular lines at a particular point. That particular point, which is with the slope of this particular thing, that is the temperature. Because here there is only one rate. It will touch this particular rate at a particular point. Whereas here you will have different rates. That is why it is like a trial and error. But in MFR, it is like only one rate. So one rate, only one conversion will come. So that particular conversion and the rate, whichever is missing, and this point, whichever point with the slope is cutting this particular thing, that is the correct temperature. It's a very important thing. Best location of an adiabatic operating line for a plug flow. You can see a trial and error search is needed. Why trial and error search is needed? Because you have different rates in plug flow reactor. And for a mixed reactor, there is no such required because there is only one rate, right? So this is the answer for one of my previous questions. One of my previous open-ended question I asked you. This is the answer. You have to now connect for which question this answer, right? I told the answer. Earlier I asked you the question. Different questions I asked you. Now I gave the answer for one of that question. So what question I gave the answer, again, it is up to you to connect the dot. I don't want to connect that. Okay. That is one. In MFR, there will be only one rate, whereas in PFR, we'll have different rates along the length of the reactor. Here you will have only one rate. This is one of the answer for one of the questions which I asked you earlier. Yeah. Okay. Can you guess what is the question now? Knowing the answer, can you guess what is the question? So you should not ask any question to you, right? No one wants to talk. Silently laughing yourself. Okay, good. So again, try to get the answers. Okay. Yeah, the other one, there is one more question which will come here. If it is going to be endothermic or exothermic, if your rate of the slope, that is, if the slope is less, what will happen? Which reactor is better? If the slope is more, what reactor is better? Again, there is one more question here, right? So here, with this particular slope, I can draw one line. This is the slope. I can draw line like this also, right? This is also one slope. This is also one slope, right? For the same exothermic reactions, right? The slope also plays a very important role. It's not that only the point here. The slope also plays a very important role. So based on that slope, this is for a very less, less slope and a very large slope, very steep line you are getting. These two are called as operating lines. This is nothing but delta Cp by delta Hr. This is for a steep slope and this is for a small slope. If this is for exothermic reaction rate, so it goes down like this, and the other rates will go up and then go down. That is what we earlier discussed. Here, one important thing is for a small slope of Cp by delta Hr, this is like this. So for a small slope, your rates also will be very less. rates also will be very less. Then it is better you go for a mixed flow. So remember, if the slope of if you are having two slopes or two, what do you call it, Cp by delta Hs at different temperatures, it's always better if the rate is very low, better go for a MFR. Now, if the rate is very steep, that is the slope is very high, then go for a PFR, right? Go for a PFR. This is a very important thing, especially for an exothermic reaction. In an exothermic reaction, if the slope is small, it is always better to go for a MFR so that your B by F naught will be less. Yes, if you are using large slope, because large slope, what will happen? Your XS will be very large. XS will be very large. You can see XS will be very large. Whereas if this particular thing, XS will be very small. Right? So large slope means large XS. Therefore, plug flow is always better. Right? So hope you understand this. Keep in mind, don't debug much into it. If you want more discussion on it, I'm open to it. But more of the discussion for a BTech student, I don't think that much is required. Right? So, more discussion, or shall I quit this? Right? Yeah. So remember, here important thing is, for a exothermic reaction, you get a positive slope. For an endothermic reaction, you get a negative slope. That is first point you have to remember, especially for a operating line. Again, if for a PFR, you have to calculate the area under the curve to calculate V by F naught. You have to calculate the area of a rectangle for MFR. That already we discussed. Now, even the slope, the value of the slope, not only the negative sign of the slope, even the value of the slope is very important. If the slope is less, then it is always better to go for a mixed reactant. But if the rate is very less, if you are putting a PFR, definitely your rate is less. Therefore, your conversion also will be less. It is waste of putting in a PFR. Now, if the slope is very more, that is slope in the sense it is Cp by delta Hr. Cp is the specific heat divided by delta Hr is nothing but the heat of reaction. If that particular value is very high, definitely put a PFR. If you put in MFR, what will happen is MFR, the rate will be suddenly down because due to the dilution. Therefore, instead of getting a high conversion, you get a low conversion for the same volume. You don't want that to happen because our main intention is to have a high conversion per less volume. If the volume is going to be same, then you want high conversion. Right? If your PFR and MFR is going to be same volume, then we want high conversion for that particular thing. Then better to go for PFR. Understand? So I'll stop here. I don't want to go much detail into it. Right? Still, a lot of discussion will be there here. In 11th spill, he stopped here. Still, if you want, again, this particular point plays a very important role. Again, this is not that easy to find out, especially in a PFR. Whereas in MFR, this point is very easy because you know what is the rate which you are looking at and you know what is the conversion which you are looking at. The meeting point of it along with the slope of this particular line. All 3 points will join at a particular point. That particular thing is nothing but your T. Okay. Now let us go for non-adiabatic. This is adiabatic, right? This is adiabatic. Your life becomes very simple. Non-adiabatic also is same like adiabatic, but extra term will come because here what you put is the input is 0. That is what you are putting. Here the input, because heat is not being added. That is what, not the heat is removed. That is what is the adiabatic. But in non-adiabatic, it's not the condition like that. So what is non-adiabatic now? Let Q be the heat added, that inlet heat is there. Whereas in the previous one, you put 0 here. Yeah, 0 here. You put 0 here. But since input is 0, that is what you are putting because the temperature is not being changed to the reference temperature. Whereas in adiabatic line, non-adiabatic, Q will be the heat added. Therefore, input is there. This is the output and this is the reaction, the disappearance. So when this particular thing is coming, if you rearrange this, XA, earlier thing is only this. Earlier thing is only this. You get minus Q because the heat which is being added, it should be removed. That is what XA. So what is this now? Earlier thing, it is the net heat. Yeah, heat needed to rise the temperature to the feed stream T2. This is Cp dash delta T. But in adiabatic, non-adiabatic, you get one extra Q. That is what it makes the difference. Now, net heat needed after the heat transfer to rise the temperature to T2. So here you are putting as heat needed to rise the feed stream to T2, whereas here the net heat still needed because already the heat is being added, still needed to raise the temperature to T2. That is why you have to subtract that divided by this is same. So here if these two are same, that is Cp dash or
Sir, he got muted.
Sir, you are muted accidentally. Sir.
sorry, muted myself. Now I am audible.
Yes, sir.
Yes, sir.
Now again not audible.
Audible, sir. You are audible, sir.
Audible.
Am I audible or not?
Audible,
Now
sir.
audible.
Okay, sorry. Earlier I think a lot of discussion is missed here. Now I am audible, right? Can I go ahead?
Yes, sir.
Yeah, this I think this temperature, this discussion you followed. What is this discussion? This you have to go for what do you call a trial and error. Whereas this particular thing, based on this and this, you can fix a point, right? So this already I discussed. So this is for low rate. If the rate is very low, then better to put a PFR, MFR, and the rate is very high. That is slope is very high. Better to put a plug flow reactor, right? So for a non-adiabatic operation, what will happen is this heat input will be there. This heat input is there. Whereas in the previous one, we are putting it as 0. Where we are putting it this particular. Here you are putting as 0 here. Okay, 0 here because the heat enthalpy, initial enthalpy is 0 because you are not increasing the temperature nor decreasing the temperature. Therefore, this 0 in non-adiabatic, this term will come into picture Q. That is what this. That is nothing but the net heat still needed after the heat transfer to rise the fluid to T2. Whereas in the previous one, it is heat needed to rise the feed stream to T2. But here the feed stream is raised by the temperature of Q. But still it should be needed to rise to the temperature T2. That is what I mentioned here. Net heat still needed after the heat transfer to rise the temperature to T2. What is the temperature? This Q, because you are adding the heat or removing the heat, whatever it is. So in your, if your Cp dash is equal to Cp, that is product is equal to the reactant, then this will be your operating line. Earlier case, you are getting only this. Earlier case, you are getting only this. Earlier case, you are getting only this, right? Earlier case, you are getting only this. But here in non-adiabatic, you get the extra term. You get the extra term of Q, right? So here important thing is the energy balance line minus Q should be there. This is nothing but like a y is equal to mx plus c. Y is equal to mx plus c. There will be a intercept or whatever it is, right? So if you are having this particular thing, this is the slope. If this is the exothermic reaction slope, this is the energy balance for adiabatic. The heat removal will be proportional to this, or the heat addition is proportional to this. Either if the heat is added, it will go like this, or the heat is removed, it will be going like this at this particular temperature. It's a very important thing because of this Q. This Q makes either to go this side or this side. If the heat is removed, then it is moving towards this with the same slope. The same slope will be changing. Whereas if the heat is added, then what will happen? This negative slope, this minus this will give less slope. Whereas if the heat is removed, Q is negative. So negative plus positive becomes positive. Therefore, the slope will be very more. Understand? So this is the important thing in the adiabatic non-adiabatic condition. The rest of the thing is going to be same. That is how this is going to add what do you call this particular thing. How you are going to do this particular thing is going to be the same. Same method is same. Only this particular slope will change depending on whether the heat is added or the heat is removed. Right. So that's all about this fourth unit. Still lot of thing will be there, which for you I don't think it is required, but for me I just gave as a notes. Now if this is a plug flow and if you want to remove the heat, this is how you have to remove the heat from the outside. So you want this line to be this is your desired temperature. So from here to here you go and then start decreasing your temperature by using coils. There is one more. If you instead of one such thing, you can go for a multiple modes. So now you see hot, warm, cold, and then cooling. So this is the desired temperature. From here you go increase. It's an exothermic reaction or adiabatic. So you come down with the same slope. This is what do you call isothermal. Right, in the sense it is isothermal. Then again go because you are heating it. Again come down. Again go. This is how you have to maintain. This is the main reason what H2SO4 you are removing out and then sending in, because you want to be at this particular point, or to have your V by F naught less. There is this is increasing temperature. There is one more decreasing temperature. This is decreasing temperature. You can put the increasing temperature also. You want a particular temperature. Now you see the temperature is being increased in the furnace. Then go and again cooled. Again it is heated. Again it is cooled. Again it is heated. So in that process, you want this desired temperature. So what you do? You go from this to here and then come down. Again go. Again come down. Again go. Again come down. How much you have to come down? That is also a very important thing. That I don't think it is much required for you here, right? So this is how you have to make the design, especially in a adiabatic and non-adiabatic conditions, especially for exothermic and endothermic. So now you might have understood why there will be intercooling in between for exothermic reactions too, because you need to be in this particular line. So for that particular line, for that particular line to be there, you want a high temperature, then come down, then go again, right? So this I don't think it is required for you, because it's very difficult for you to understand. So if the time permits, I will discuss about this bit later, right? Now for a MFR, you see how we have to include this particular thing. This is the design expression for MFR. Now, if you put Ca naught Xa by Ra is K Ca naught first order, K into Ca. So K Ca naught this. So K Ca naught cancels. So you are getting this. Now, if you write in terms of Xas, K tau by 1 plus K tau. This is what earlier itself we discussed. Now, for a what do you call heat effects, if the temperature is increasing, this K will change. This is the temperature. Now, if you put this here, then what will happen? Kt is the exit temperature. So K naught tau e power minus E by RT KT2 divided by K naught T, this particular thing. This is your material balance line. This is your material balance line. Now, what is the energy balance line? The steady state energy balance line is XA is Cp delta T by delta HR. What is delta T? T2 minus T1. So T1 is the feed temperature, T2 is the temperature to which you have to rise. So based on this equations, we need to draw that is energy balance line. You give it different temperatures, calculate XCS. So you will get a curve like this. You get a curve like this for exothermic reaction, different curves at different temperatures. Then we'll try to fix locus of this particular thing. So how much you have to go this based on this. So you put a line and then go for this and see whichever is cutting. Then based on that, you draw the graph and calculate V by F naught. This is for mixed reactor. Yeah, this is for mixed reactor. That is what the same thing I am just showing you. Right. So like that you can do for a plug flow reactor also. Like that you can do for a plug flow reactor also. Right. So based on that, they will be giving some problems here. Please try to do these problems and the exercise problems of 5. Right. That 5 exercise problem, what do you call not exercise, that is worked out problems, and this 10. Please try to do more problems, you will understand more, right? This is called as a bifurcation curve, so which I don't think it is required for you. Here is very important point. This is the unstable point. This is the energy balance curve, and this is the material balance curve. The moment you want to stay here, but if you increase the slight temperature, what will happen? Your shoots up to a very high temperatures, because the removal is much more than this particular thing, or then you want to operate the reactor at this point, either it goes to this point, this temperature, or this temperature. If you are coming down, this is what we call as multiple steady states in reactors. So you want to operate at this particular point, even a small change in temperature, it will go to another steady state. Even a small decrease in temperature, it goes to another steady state. Right? So for the same what do you call things, energy balance, you for the same, this is the material balance curve, and this is the energy balance. So different points will have the same thing. That is what we call as multiple steady states. In technical terms, we call as a bifurcation curves. I think these are all you can study when you are going, especially in what do you call MTech. This we call as a runaway reaction. The moment it goes here, you cannot control this temperature because it suddenly goes from this temperature to this. The reaction will run away. That means without any control. You cannot have any control over this. Either this particular temperature, again a small decrease, it goes to a very less temperature where the reaction won't happen at all. This is what we call as a runaway reactions. Okay, I'll stop here and I'll stop the unit also. So based on that, here 10 questions are there. This 10 and that 5 problems which is worked out in the 11th spill. Try to do and then submit. Okay, this is for your 4th assignment. Again, I'm telling you, please try to do a lot of problems. Yet, since due to the lack of time, I'm not doing problems, because the problems, it takes long time because you have to draw the graph. Yeah, please try to do. If any difficulty is there, you let me know. Okay. I'll stop here. Guru, I think you can take the attendance. I'll just tell how many people are there.
Sure.
57 is there. I think 56 should be there. 9 people will be absent. Yeah, any doubt today's lecture? This is all about the 4th unit. I just want to complete, that is start 5th unit from next week. Yeah, any other query? No? If there are no queries, I'll stop the recording now. I'll stop the recording and